Imagine falling into a place where time slows to a crawl, space twists into impossible shapes, and the laws of physics as we know them begin to dissolve, a place so extreme that even light cannot escape. For centuries, black holes were dismissed as mathematical absurdities, curiosities hidden inside equations. Today, they are no longer theoretical. We have photographed them, detected their collisions, and listened to their echoes across the universe. And yet, black holes may be only the doorway. Beyond them may lie wormholes, shortcuts through space-time, and perhaps even bridges to other universes. What once belonged to science fiction is now emerging from the heart of modern physics to most of human history. Gravity was the most familiar and least mysterious of forces. Apples fell, planets moved, stars glittered in the night sky, and gravity seemed gentle, predictable, almost comforting. Yet hidden within the equations that describe gravity lies a terrifying conclusion. If enough matter is squeezed into a small enough space, gravity does not merely pull, it dominates. It overwhelms all other forces, crushing matter, bending light, and reshaping space and time themselves. This is how black holes are born, not as exotic monsters from imagination, but as inevitable outcomes of the laws of physics. A black hole begins its life as an ordinary star burning nuclear fuel in a delicate balance between two opposing forces. On one side, gravity tries to crush the star inward. On the other, the energy released by nuclear fusion pushes outward. For millions or billions of years, this balance holds. But when a massive star exhausts its fuel, the outward pressure suddenly collapses. Gravity wins decisively. The star implodes, collapsing under its own weight. In the most extreme cases, nothing stops the collapse. Not atoms, not nuclei, not even the fabric of space-time itself. The result is an object so dense and compact that it creates a region from which nothing can escape. This is not because black holes are unusually aggressive or actively pulling everything toward them. In fact, if our sun were replaced by a black hole of the same mass, the planets would continue orbiting almost exactly as they do now. The terror of a black hole lies not in its reach, but in its depth. Once you get too close, gravity becomes inescapable. Space curves so steeply that all paths lead inward. The black hole does not suck you in. The universe simply gives you no other direction to go. At the heart of a black hole lies an idea that pushes physics to its breaking point. According to general relativity, all the mass of the collapsed star is crushed into a single point of infinite density known as a singularity. At this point, space and time lose their meaning. Distances shrink to zero, densities become infinite, and the equations we rely on stop working. This is not just a technical problem. It is nature telling us that our understanding is incomplete. Black holes are not merely objects in space, they are signposts pointing toward a deeper theory of reality. What makes black holes even more astonishing is their role in shaping the universe. They are not rare anomalies scattered randomly through space. At the center of almost every galaxy, including our own Milky Way, lies a supermassive black hole containing millions or even billions of times the mass of the Sun. These giants act as cosmic engines. As matter falls toward them, it heats up, glows, and releases vast amounts of energy. Jets of particles shoot out at nearly the speed of light, influencing the formation of stars and entire galaxies. Far from being destroyers, black holes are architects of the cosmic structure. Yet the most profound mystery begins at the boundary surrounding a black hole, a surface known as the event horizon. This is not a physical wall or a glowing shell. It is a mathematical boundary in space-time. Cross it, and escape becomes impossible. From the outside, an object falling toward a black hole appears to slow down, its clock ticking more and more slowly as it approaches the horizon. To a distant observer, the object never quite crosses. It freezes in time, fading and reddening until it disappears. Time itself seems to stop at the edge. From the perspective of the falling object, however, something very different happens. It crosses the event horizon without noticing anything special. There is no sudden jolt, no invisible barrier, no alarm announcing the point of no return. The laws of physics locally appear normal, at least for a while. This strange duality reveals one of the deepest truths of modern physics. Time is not absolute. It flows at different rates depending on gravity and motion. Near a black hole, time is stretched to extremes, proving that it is as flexible as space itself. The event horizon represents more than a point of no escape. It is a boundary of information. Once something crosses it, information about its state seems to vanish from the observable universe. This creates a paradox that has haunted physicists for decades. According to quantum mechanics, information can never be destroyed. It can be scrambled, hidden, or transformed, but it must always exist. According to classical descriptions of black holes, information is lost forever once it crosses the horizon. Both theories are spectacularly successful, yet here they appear to contradict each other. This conflict has forced physicists to rethink the nature of reality. One possible resolution is that information is not lost, but encoded on the surface of the black hole itself, spread across the event horizon like a cosmic memory. This idea has led to the holographic principle, which suggests that all the information contained within a volume of space can be described by information on its boundary. In this view, the universe itself may be a kind of hologram where the deepest truths of reality are written not in volumes but on surfaces. The event horizon also teaches us that the universe has limits to what can be known. There are regions of space-time that are forever inaccessible, not because of technological shortcomings, but because of the structure of reality itself. This is a humbling realization. Even with perfect instruments and infinite patience, some information will always remain beyond our reach. Yet, rather than diminishing science, this boundary enriches it. It forces us to ask sharper questions and develop deeper theories. What makes black holes especially powerful as scientific tools is that they sit at the intersection of gravity, quantum mechanics, and cosmology. They are the only known objects where all three must be considered simultaneously. In studying them, physicists are not merely cataloging exotic phenomena. They are probing the ultimate laws that govern space, time, and matter. Every insight gained from black holes pushes us closer to a unified description of nature. Black holes also challenge our emotional intuitions. They sound terrifying, destructive, final, but in reality, they are natural consequences of stellar evolution. As essential to the universe as stars themselves, they recycle matter and energy, regulate galactic growth, and perhaps even play a role in the birth of new universes. They remind us that creation and destruction are not opposites in nature, but partners in a larger process. At the edge of a black hole, the familiar categories of past, present, and future begin to blur. Inside, according to theory, time and space may even switch roles, forcing everything to move toward the singularity as inevitably as we move toward tomorrow. This inversion shatters everyday intuition and reveals how deeply our sense of reality depends on the gentle gravitational environment we evolve within. Black holes, then, are not merely cosmic curiosities. They are windows into the extreme, places where the universe reveals its deepest secrets by pushing its own laws to the limit. They show us that gravity is not just a force, but a geometry. That time is not universal, but local, and that the universe is far more flexible, mysterious, and astonishing than it appears from the quiet surface of everyday life. Once we cross the event horizon in our imagination, physics takes us into a realm where familiar concepts no longer behave as expected. According to classical general relativity, everything that falls into a black hole is inevitably drawn toward the singularity at its center. This is not merely a place in space, it is a moment in time. Oh, inside a black hole, space and time exchange roles, just as you cannot stop moving forward in time in everyday life. Inside a black hole, you cannot stop moving toward the singularity. It is not a destination you might reach. It is a future you cannot avoid. This realization alone reveals how radically different reality becomes under extreme gravity. The singularity represents a breakdown, not just of matter, but of knowledge itself. Density becomes infinite, space-time curvature becomes infinite, and the equations that successfully describe planets, stars, and galaxies collapse into meaningless symbols. This is not because nature has failed, but because our theories have reached the edge of their validity. General relativity works beautifully on large scales, while quantum mechanics excels at describing the microscopic world. At the singularity, both are required simultaneously, yet they refuse to cooperate. This tension tells us that a deeper theory must exist, one capable of uniting gravity with quantum mechanics into a single framework. Rather than being an embarrassment, this breakdown is a gift. It provides a clear signal pointing toward new physics. Black holes act as natural laboratories that force us to confront unanswered questions. What is space-time made of at the smallest scale? Is it smooth and continuous or granular and quantized? Does the singularity truly exist as an infinitely dense point, or is it replaced by something more subtle when quantum effects are taken into account? Some theories suggest that matter never collapses to a point but rebounds or transitions into another phase of existence hidden behind the horizon. Others propose that space-time itself dissolves into a quantum foam, where the classical notion of location loses meaning. As strange as this sounds, such ideas are not arbitrary. They arise from attempts to reconcile well-tested theories under extreme conditions. In these scenarios, the singularity is not the end of the story, but a signpost marking the limits of classical thinking. It may be that what we call a singularity is merely a placeholder for physics we do not yet understand, much like the center of an atom once appeared mysterious before the advent of quantum theory. This brings us naturally to the concept of wormholes, one of the most fascinating implications of Einstein's equation. When space-time is allowed to curve and warp, it can also, in principle, connect distant regions through tunnels. A wormhole is not a hole punched through space, but a bridge formed by space-time itself. Two distant points, which might be separated by millions of light years in ordinary space, could be neighbors through a wormhole. Travel through such a structure would appear to violate the cosmic speed limit, but in reality it would not. Nothing moves faster than light locally. Space-time simply takes a shortcut. Wormholes arise mathematically as valid solutions to the equations of gravity, just as black holes do. For decades, they were dismissed as curiosities, unstable and unphysical. And indeed, according to known physics, most wormholes would collapse instantly, pinching off before anything could pass through. To remain open, they would require exotic forms of matter with negative energy density, something not found in ordinary matter. Yet quantum physics allows small amounts of negative energy to exist under special conditions, suggesting that nature does not outright forbid such structures. It merely makes them extraordinarily difficult to create and sustain. The existence of wormholes hints at a universe that is far more interconnected than it appears. Distance, which seems absolute in everyday experience, may be negotiable at the deepest levels of space-time. This idea reshapes how we think about separation, travel, and causality. If wormholes could exist naturally or be engineered by advanced civilizations, they would not merely revolutionize transportation. They would redefine what it means for two events to be far apart. Even more astonishing is the relationship between wormholes and time, because space and time are intertwined. Manipulating one inevitably affects the other. A wormhole whose two ends experience different gravitational environments or different velocities could connect not just distant places, but different times. In theory, this opens the door to time travel, not the cinematic fantasy of stepping into a machine and vanishing in a flash of light, but a subtle, relativistic phenomenon emerging naturally from the geometry of space-time. This possibility immediately raises paradoxes. What happens if information travels back in time? Can cause precede effect? Physics responds not with easy answers, but with constraints. Some theories suggest that the universe enforces consistency, preventing paradoxes through self-correcting mechanisms. Others propose that time travel would create branching timelines, preserving causality by allowing multiple histories to coexist. In either case, the message is the same. The universe is far more flexible than common sense suggests, but not lawless. What makes wormholes especially intriguing is their connection to quantum theory. Recent research suggests that entangled particles, which remain correlated across vast distances, may be linked by microscopic wormholes. This does not mean information travels through them in any classical sense, but it hints at a deep connection between geometry and quantum information. Space itself may emerge from networks of quantum entanglement. In this view, wormholes are not exotic exceptions, they are the visible expression of a deeper quantum structure underlying reality. This idea turns our understanding of space-time inside out. Space is no longer a fundamental stage on which events occur. It becomes a derived concept emerging from more primitive quantum relationships. Black holes and wormholes, then, are not anomalies at the edges of physics. They are windows into its foundation. They show us that geometry, information, and quantum mechanics are inseparable aspects of the same underlying reality. The implications are profound. If space-time can connect distant regions through wormholes, and if singularities signal transitions rather than endings, then the universe may be far more navigable and far less final than we once believed. Creation and destruction blur into transformation. What appears as collapse from one perspective may be emergence from another. A black hole may not be a cosmic grave, but a doorway into new physics. Perhaps even new regions of existence governed by different rules. In this light, black holes and wormholes are not merely objects to be feared or exotic curiosities to be admired from afar. They are messages written into the fabric of the universe, telling us that our current understanding is only a chapter, not the whole book. They challenge us to move beyond intuition, to accept that reality is built from principles that operate far outside everyday experience, yet remain accessible through reason, mathematics, and imagination. When gravity becomes extreme, the universe reveals something deeply counterintuitive about time itself. In everyday life, time feels absolute, marching forward at the same pace for everyone, everywhere. But this is an illusion born of weak gravity and slow motion. Einstein showed that time is elastic. It stretches and contracts depending on speed and gravity, and nowhere is this effect more dramatic than near black holes. As you approach one, clocks slow down relative to the rest of the universe. From a distant observer's point of view, time near the black hole almost grinds to a halt. This is not a trick of perception. It is a measurable physical effect confirmed every day by satellites that must correct for time dilation just to keep GPS working. Near a black hole, this stretching becomes extreme. A person hovering close to the event horizon would see the rest of the universe race forward. Stars would age, galaxies would evolve, and the distant future would unfold in minutes. This is time travel of a very real kind. It is not traveling into the past, but into the future, achieved not by imagination, but by geometry. The universe itself provides the mechanism. Gravity bends time, and black holes bend it to the breaking point. This realization changes how we think about time travel. The universe does not forbid it. In fact, it already allows one direction of it. Traveling to the future is not speculation, it is a consequence of relativity. Astronauts aboard the International Space Station age slightly more slowly than people on Earth. The effect is tiny but real. Near a black hole, the effect becomes enormous. A journey lasting hours for the traveler could correspond to centuries passing elsewhere. The laws of physics permit this without paradox or contradiction. Time, it turns out, is negotiable. Wormholes take this idea even further. Because they connect distant regions of space-time, they can also connect regions with different temporal histories. If one mouth of a wormhole experiences strong gravity or high acceleration relative to the other, time will flow differently at each end. Step through, and you could emerge at a time earlier than when you entered, at least from an external perspective. This is where the notion of traveling into the past arises, not from fantasy, but from the mathematics of space-time itself. Immediately the mind rebels. Paradoxes spring up. Can you change the past? Can cause follow effect? Physics responds cautiously. Some theories suggest that the universe enforces consistency. Events adjust themselves so that paradoxes never occur. You might travel to the past, but only in ways that ensure history remains unchanged. Other approaches suggest that traveling to the past would create new branches of reality, preserving causality by allowing multiple timelines to exist simultaneously. In both cases, the message is clear. Time travel, if possible at all, is tightly constrained by the laws of nature. What is remarkable is not whether time travel will ever be practical, but what these ideas reveal about time itself. Time is not a universal river flowing independently of the universe. It is woven into space-time, shaped by matter, energy, and motion. Black holes and wormholes do not break time, they expose its true nature. They show us that the future and past are not rigid categories, but features of a dynamic geometry. As we push deeper into these questions, another mystery emerges, one that strikes at the heart of both gravity and quantum mechanics, the fate of information. When something falls into a black hole, all the details that describe its structure, composition, and history seem to vanish behind the event horizon. Classical physics suggests that this information is lost forever. But quantum mechanics is uncompromising. Information cannot be destroyed. This conflict is not academic, it threatens the consistency of physics itself. The paradox becomes sharper when we consider that black holes are not eternal. Over immense timescales, they slowly evaporate through a quantum process now well established. As they lose mass and eventually disappear, the question becomes unavoidable. If the black hole is gone, where did the information go? If it truly vanished, quantum mechanics would be wrong. If it escaped, then our understanding of Black holes must be incomplete. This problem has driven some of the most profound advances in theoretical physics. One surprising outcome is the realization that black holes behave like thermodynamic objects. They have temperature, entropy, and even a kind of surface area that encodes information. The entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This is astonishing. It suggests that all the information about what falls into a black hole is somehow stored on its surface, not in its interior. From this idea emerges a radical new view of reality. The event horizon acts like a hologram, encoding a three-dimensional interior on a two-dimensional surface. This insight led to the broader holographic principle, which proposes that the entire universe may operate this way. The reality we experience in three dimensions could be encoded on a distant boundary, like a cosmic projection. Space itself may be an emergent phenomenon, arising from deeper informational processes. In this framework, black holes are not destroyers of information, but processors of it. They scramble information beyond recognition, spreading it across their horizons in a highly entangled form. To an outside observer, the information is not lost, just transformed. It is hidden in correlations so complex that reconstructing it would be unimaginably difficult, but not forbidden. The universe keeps its books balanced, even in the most extreme environments. This view reshapes how we think about reality at a fundamental level. Information becomes as basic as matter and energy. The universe is no longer just a collection of particles moving through space and time. It is a vast network of information, encoded, transformed, and conserved. Black holes, once thought to be the ultimate sinks, become key players in revealing this deeper structure. The connection between black holes information and quantum mechanics goes even further. Recent ideas suggest that space-time itself may be built from quantum entanglement. Regions of space are connected because the underlying quantum states are entangled. In this picture, wormholes and entanglement are two sides of the same coin. Geometry emerges from information. Space is not fundamental, relationships are. This is a stunning reversal of perspective. For centuries, space and time were considered the stage on which physics unfolds. Now they appear to be actors themselves, emerging from more primitive quantum processes. Black holes, by pushing space-time to its limits, expose this hidden layer of reality. They force us to abandon the idea that geometry is fixed and accept that it is dynamic, emergent, and deeply tied to information. What ties all of this together is a sense that the universe is far more unified than it appears. Time travel, information conservation, black holes, and wormholes are not separate curiosities. They are facets of a single, deeper structure waiting to be fully understood. Each paradox is not a failure but a clue. Each contradiction points toward a more comprehensive theory that will one day reconcile gravity and quantum mechanics into a single, elegant framework. In exploring these ideas, we are not indulging in speculation for its own sake. We are following the logic of the universe where it leads, even when it challenges intuition. The cosmos has revealed again and again that it is stranger than expected, yet governed by laws of extraordinary coherence. Black holes and wormholes are not exceptions to those laws. They are the places where the laws speak most clearly, telling us that time can bend. Information endures, and reality is far deeper than the surface we perceive. As we contemplate black holes and wormholes, the question naturally arises, could these cosmic phenomena connect us to other universes? This is not mere science fiction, but a serious consideration emerging from modern cosmology. Some theories suggest that black holes may act as gateways, not merely to distant regions of our own universe, but to entirely new universes with their own physical laws. According to the mathematics of general relativity, the interior of a black hole could curve space-time so dramatically that it pinches off, forming a new region of existence beyond our perception. From the outside, it looks like a death, a disappearance of matter and energy. From a higher dimensional perspective, it may be a birth a new universe emerging from the collapse of a star in our own. This perspective radically transforms how we view creation itself. Our universe, vast and seemingly self-contained, may have been born inside a black hole residing in a parent universe. Each black hole, then, is not simply an endpoint, but a seed of cosmic renewal. This idea reframes the life cycle of universes. Stars collapse, black holes form, and from their singularities, new universes might emerge, each with its own initial conditions, and perhaps its own laws of physics. What seems destructive from one vantage point is generated from another, suggesting that the universe and perhaps multiverses operate as self-replicating systems. The implications extend even further. If black holes can spawn new universes, then the constants of nature we observe may be part of a selection process. Only universes with certain physical parameters allow stars to form, matter to coalesce, and black holes to create new universes. In this view, our universe may appear fine-tuned not by accident or design, but because universes capable of producing black holes are naturally favored. This idea, known as cosmological natural selection, provides a framework for understanding why the laws of physics are so remarkably suited to the emergence of complex structures, including life. The multiverse, in essence, becomes a vast evolutionary system exploring all possibilities, and black holes are the engines driving that exploration, even if direct travel to other universes remains beyond our reach. Studying black holes and wormholes teaches us profound lessons about reality. They reveal that space-time is flexible, that the flow of time is relative, and that information is conserved in ways we are only beginning to understand. They suggest that our universe is not isolated, but connected in ways that may extend beyond our current comprehension. Each black hole becomes a laboratory for testing these ideas, providing a natural setting where the extremes of physics converge. By observing the behavior of matter near event horizons, by detecting gravitational waves from colliding black holes, and by analyzing high-energy phenomena in their vicinity, we gather clues about the very fabric of reality. This also reframes our understanding of the ultimate fate of the universe. Far from being a static or terminal cosmos, the universe may be dynamic, continually generating new regions of existence. Galaxies, stars, and black holes are not endpoints. They are part of an ongoing process of cosmic evolution. The singularities at the centers of black holes, once thought to mark destruction, may instead be portals to the creative potential of the cosmos. Matter is transformed, energy is redistributed, and in some speculative, but mathematically plausible ways, entire new realms are born. Reality, in this vision, is not finite but generative, endlessly exploring possibilities beyond the confines of our perception. The study of black holes and wormholes also intersects with the deepest questions of physics: how gravity relates to quantum mechanics, how space-time emerges from fundamental information, and how the universe preserves consistency even under extreme conditions. Black holes challenge our understanding of determinism and causality. Wormholes suggest that connections exist beyond ordinary space and time. Together, they imply that the universe is far more interconnected and subtle than it appears. Information, matter, energy, and geometry are not separate entities. They're intertwined in a complex dance that underlies all existence. By probing the extremes, we glimpse the underlying unity of the cosmos. Moreover, black holes invite us to reconsider our philosophical assumptions. They suggest that what we perceive as endings, death, collapse, disappearance may, in a larger context, be transformation. They teach us humility, showing that our intuition, honed in the gentle gravitation fields of Earth, is ill-equipped to grasp the extremes of the universe. They also inspire awe, revealing the profound beauty and elegance of natural laws operating under conditions far beyond our everyday experience. In contemplating them, we are not merely studying objects, we are engaging with the architecture of reality itself. As we contemplate wormholes, the same lesson emerges. They hint at a universe that is not rigid or constrained, but flexible, navigable, and deeply interwoven. They suggest that distances, and perhaps even times, are negotiable under the right conditions. While the practical creation or traversal of wormholes may be centuries or millennia away, if ever possible, the theoretical framework they provide reshapes our imagination. They encourage us to think beyond the obvious, to question the limits of what can exist, and to explore the consequences of the laws of physics when pushed to their extremes. Wormholes are not merely speculative curiosities. They are profound statements about the potential structure of reality. The study of black holes, wormholes, and their relationship to the broader universe also highlights a fundamental theme. The universe is not designed to be simple or easily understood. It operates according to deep principles, many of which remain hidden from direct observation. Each discovery is a window into these principles. The equations that describe black holes hint at symmetries, connections, and constraints that transcend our immediate experience. They suggest that reality is both stranger and more beautiful than common sense allows. By studying them, we are not only uncovering how the cosmos behaves, but also how deeply coherent and interlinked it is at its most extreme scales. In the end, black holes and wormholes teach us that the universe is alive with possibilities. They reveal that destruction and creation are two sides of the same process, that time and space are malleable, and that information, the fundamental currency of reality, is never truly lost. They hint at connections to other universes, suggesting that our cosmos may be one of many, a single bubble in an eternal, ever-replicating multiverse. And through all of this, they remind us that human curiosity is our greatest tool. By pushing the boundaries of observation, mathematics, and imagination, we continue to unravel the profound mysteries of existence, revealing a universe that is at once terrifying, magnificent, and infinitely more expansive than we could have ever imagined. In conclusion, black holes and wormholes are far more than cosmic curiosity. They are gateways to understanding the deepest laws of the universe. They reveal that space and time are flexible, that information is conserved in extraordinary ways, and that the universe may be far more interconnected and generative than we ever imagined. These phenomena challenge our intuitions, stretch our imagination, and invite us to explore the boundaries of reality itself. They show that what we perceive as endings, collapse, disappearance, or destruction may, in a larger cosmic context, be transformations, gateways to new possibilities, or even other universes. By studying them, we gain insight not only into the cosmos, but into the fundamental structure of reality, revealing a universe that is dynamic, mysterious, and endlessly awe-inspiring. Thank you to all the viewers for joining this journey into the mysteries of black holes, wormholes, and the universe. Your curiosity keeps the spirit of discovery alive, and your willingness to explore the unknown fuels the endless adventure of science. Keep questioning, keep imagining, and never stop reaching for the stars.